So I have the pleasure to introduce you Thias Gunn. He's associate professor in computer science at DTAI labs of Catholic University of Leuven in Belgium. His expertise is in hybridization of machine learning system with constraint solving. He was awarded the prestigious ERC Consolidator grant in 2021 to work on conversational human-aware technology for optimization. Thank you so much for accepting our invitation. We're very happy to hear you today.
Yes, thank you very much also for the invitation. So I'm here, I'm actually as part of the CRM thematic series on combinatorial machine learning. So I'm a Simon's visiting professor until June. And I'm happy to take this opportunity to speak to multiple of you. And so with this talk, I'll give a bit of an overview of the things that we've been working on. So I'm indeed from computer science, from an AI lab. So I have this AI way of looking at problems, including combinatorial optimization problems. So what do I mean with combinatorial optimization? I especially like fully discrete problems, for example, vehicle routing and scheduling and packing and other sometimes more toy or more theoretical problems. And so, as we all know, there's been tremendous progress in the efficiency of combinatorial solvers. And this is from a paper where they took instances that could not be solved 10 years ago by MIP solvers. Then many of those are now solved in mere seconds 10 years later. Also in the Boolean satisfiability community. And this is from 2022, I think. And they just plotted like all of the winning solvers year after year. And you can see this continued progress on faster and more efficient solving. Okay, so how do we use these solvers? Well, as you know, we often follow a declarative paradigm where we model a problem in terms of decision variables and objective function constraints. And then we use these highly efficient solvers. And so in a lot of our work, we don't care too much about the actual solving technology. So we developed this library called CPMPy, where you can formulate your problem at a high level, with integer variables and so forth, and then it will be translated to CP solvers or ILP solvers or pseudo Boolean solvers or SAT solvers. And so you can really try a bunch of them and see what suits you best. For many of what we do, yeah, an automatic encoding is sufficient. Okay, so far so good. But then if you want to start using this in practice, then and you talk to a company, for example, they have some combinatorial optimization problem. Then the question is, where does this magic model actually come from? And so the answer is that that model is based on a problem description, which itself is only a model, right? An approximation of the true problem that this company or this group of individuals is trying to solve. And that's where things tend to break down. So here, beautiful research, here, also beautiful research, and here, I think there's also beautiful research. But like from an AI perspective, there's a lot of opportunities here, not to assume that the model is given, but to see if we can open that box a bit and also learn more from the environment, from the context. So that's what I mean with underspecified combinatorial optimization problems. And so some of the input of the problem that you're trying to solve will not be given as a formal specification as a constraint model. And this could be that some of the parameters will have to be estimated from historical data. This could be that there's preferences that are not given explicitly, but that you want to extract from historical solutions. Or this could be that even some of the structure of the problem is not known yet, not given to you yet, and you want to extract it in some way. Okay. So that's what I mean with underspecified combinatorial optimization problems. If we then take a bit more of an AI view on this, then actually the kind of approach that I really like is where, there's a problem that you want to solve, and part of it is what we call explicit knowledge. So it's easy to formalize, for example, the number of vehicles you have, the precise location of your clients, and so forth and so forth. But then another part of the problem is actually very difficult to formalize and to put into constraints. It's more implicit knowledge, for example, preferences, for example, driver familiarity. And so this is typically hard to formalize exactly in constraints. However, it might be easier to learn, especially given enough data. So that's this. Within AI, onto this sometimes called neurosymbolic. Neurosymbolic AI, if you combine these things, because within AI we have two large families. Everything that has to do with statistical learning, which is about making predictions and also data and getting a fast answer. And then everything that has to do with formal reasoning, for example, Boolean satisfiability or integer linear programming. So it focuses on knowledge, logical inference, and it's typically smaller. So neurosymbolic AI is at the integration of these two. And a lot of what I do can be looked at that from that perspective. And so the menu of today, so I'll talk about some of these. If you were at the CRM talk 2 weeks ago, I changed some of the items on the menu to be more seasonal to the audience at hand. And so we'll dive straight into one of the problems that you're very familiar with, this contextual stochastic optimization. And so from a contextual stochastic optimization point of view, you have a combinatorial optimization problem, but then some of the parameters, you still have to estimate it from correlated data. So we'll first solve a prediction problem that will give you, well, so given a machine learning model, you will then make some predictions and feed that into that. And then the question is, how do you actually learn that? And then in the nice survey, there's the sequential learning and optimization where you train this one independent of the downstream problem, and then the more integrated learning optimization where you do the learning in an integrated way. So what's interesting about this problem? So from a standard machine learning point of view, and doing the sequential learning part, that and standard ML typically assumes plenty of data. It's easy to evaluate how your machine learning model is doing on that specific task, and many well-known loss functions are available. But if you then take this downstream problem consideration into account, then actually if you want to evaluate how good your predictions are, for example, you're predicting the energy price at each of the coming hours for a 24-hour block, and then you're going to solve a scheduling problem, energy-aware scheduling problem over that. Well, to actually evaluate your quality on the downstream energy-aware scheduling problem, this requires you to solve the problem and then measure the quality and the error. And so if you're going to do that, then the question is, okay, so is your traditional machine learning loss function that treats each of the time slots independently, mean square error, is that actually sufficient? Or can you somehow use a downstream loss function? And there's other challenges in terms of amount of data that's available for in combinatorial optimization. 100 or 1,000 instances is typically considered a lot. Okay, so what about stochastic optimization? Indeed, contextual stochastic. So the work that I've worked most on, then the coefficients are only in the objective, and more specifically, they're linear in the objective. And so that means that if you get a wrong prediction in the objective, then the only thing that changes is the actual estimate of the cost of that solution. And so there is no recourse action, there is no infeasibility, there is nothing. You just pay money or a cost. And so that there's no recourse action per se, there's only regret. So it's a single stage, you could see it as a single stage stochastic optimization problem. And furthermore, when it's linear objective and the expected value of the sum is a sum of the expected values. And I know there's other settings, and I'll touch a little bit on it soon, but this is a setting that I've worked most on. So you don't need stochastic optimization in this case. Okay, so let's look at that evaluation. So this is one of the worst cases that we've had so far. The green line here is mean square error. So we're doing sequential learning and optimization here. So and we see that as the error gets lower and lower and lower, you would think that your predictions get better and better and better. But if you look at the downstream error, so the regret and the cost of following the predicted value instead of the unknown true value, that actually goes up and up and up. And so it means that, okay, so why is this happening? And so what's actually happening is that when you're solving your downstream problem, you're actually taking multiple predictions into account. And so what you have is a joint error because you're doing joint inference, you're doing inference reasoning over each of these predictions. And so some errors are worse than others. So can we use that as a learning signal? It's a reasonably well-studied problem in the past 5 years. Yeah, so that's another summary. So mean square error treats each of the individual errors, but some errors actually worse than others. That's a typical example that we use. So we also have a survey paper, and there we use this little example to show it. So this is a 2-item knapsack problem. And so the true values is that for one item, you should put it 3, for another 2.5, meaning that you should take the 3 item here. And then if you look at all of these points, and so clearly they're mispredicting, so they will have a different mean square error than this true point. However, it doesn't change the decision that is being made. So even if you mispredict in this direction or in this direction, you're still choosing item 2 here. And so your regret is 0. While if you compare these 2 points, then they're all at the same distance from the true point. So their mean square error is the same. However, this point jumps to the other line of the decision boundary. And so they have a different regret. So that's another way of looking at it. I know some of you are very familiar with this, but okay, and so then that leads to the question, okay, can we actually do this end-to-end decision-focused learning? So given our neural network, it will predict cost vectors, we solve some contour optimization problems, some agreeing over a potential exponential number of solutions. And then can we then compute a loss function that we can backpropagate back over? And so the computational challenge here is that if you want to use gradient descent, then as we've seen in this little toy example, and so you might change your weights, your learned weights a bit, and actually your decision doesn't change at all. And then if you're at this point and you change weight just a little bit, you jump to a completely different discrete solution. So that means that either the solution doesn't change and the gradient is 0, or it jumps to another one and then the gradient is undefined. Right, and so in this survey paper called Decision-Focused Learning, Foundation, State-of-the-Art, Benchmark, and Future Opportunities, we've looked at this specific problem, so in the objective function, so a subset of stochastic contextual optimization. And there we've grouped it into four different categories of methods. I think an important distinction is that the top 2, they make an assumption on the type of constraint combinatorial optimization solver that you use, namely a primal dual solver, where you have access to the dual values and to the optimality conditions. While these methods, they do not place any assumption on the solving technology and can be used with any type of solver. Okay, so I'll again, I know some of you are very familiar, so I'll just share a bit of it and then I'll jump to some other things. So I think one of the most basic approaches of this analytical differentiation over the optimization mapping is in the continuous unconstrained problem. So you have a continuous and unconstrained problem, and then there's this nice work earlier, I think, Gould 2016, where they say, okay, if you want to differentiate over this, well, what you can do is you can take the first order optimality conditions, and then you can do, and that gives you because there's a relation from the predictions to the optimal solution, but there's no direct mapping from the optimal solutions back to the coefficients. But if you take these optimality conditions, then you can do implicit differentiation over that, as long as your f function is twice differentiable. Okay. And I think a lot of the other works build on that. So there's been works on continuous constraint using KKT optimality conditions or homogeneous self-dual optimality conditions. Also for mixed integer programming, where you can add either a quadratic penalty to make it twice differentiable or a log penalty, like in interior point solving, and so forth and so forth. Lots to discuss that I'm not going to do. Another method I want to highlight is the very well-known SPO plus loss function. So this one places no assumption on the solver used. It proposes a convex surrogate, which is an upper bound on regret, and it has a very simple and very elegant subgradient, and namely you solve the problem with your true cost vector, and then you solve it with a perturbation, you take the true cost factor, but then you take your predicted cost factor 2 times the predicted cost factor, and then you subtract the true cost factor from that. And if you then take these two solutions and you subtract them, that gives you a subgradient for each of your decision variables. This is very elegant, and it also works very well. In fact, it's one of the few methods that actually uses the true cost when it's doing this, this differentiation. Many of the other methods are more inverse optimization, like they only use the solution, but not the true costs. Which also means that it requires knowing the true cost. Okay. Okay, and then the third category is which is smoothing by random perturbation. And so the idea is that you can perturb the cost factor by sampling from some well-chosen distribution. And so what's the main, there's a range of papers that do this in different ways, also perturbed Fenchel-Young, for example, and so forth. And so the idea is that if you're here and you perturb your prediction a bit, then you might, in some of the cases, you might jump to this part of the prediction, in some of the cases, you might jump here. And so the further away that you're from such a jumping point, the smoother, the closer your estimate will be to that value, and the closer you are, the sharper it is, but it's always continuous. By taking these samples, it is always continuous, and so you can smoothly differentiate over it. And so not only is this solver agnostic, but you can also use it as a layer. So even if the output of your combinatorial optimization problem is then the input to another neural network, you can still differentiate over that first one and then over this to your predictions. Okay, so this so far has only been about predictions in the cost factor, which is what our part of the survey is about. So what would be the most generic formulation possible? What if you make no assumptions on whether it's in the coefficient, in the objective function, whether it's in the constraint, left-hand side, right-hand side, really no assumption whatsoever. And so we have some work called score function gradient estimation to widen the applicability of this approach. And so the idea is that if you assume any kind of loss function or cost function, including a post hoc regret, so one that includes feasibility correction in case you're making prediction constraints, what could you do? And so within machine learning and related to reinforcement learning, there's a method called score function gradient estimation in the reinforce method, and that one is also very applicable here, and it's also very elegant. So what do you need to do? First of all, you're not going to predict a point estimate, which is what we've done so far because it was the sum of the expected values, right? So in this case, you're not going to do that. You're going to predict a distribution. And it's going to be a very simple distribution. So in our case, what we did is it's just a simple Gaussian distribution. So you're not just going to predict the expected value, the mean, but you're also going to predict the variance, so 2 parameters. Okay, and then you get this loss, which I think is the general formulation of a contextual stochastic optimization. And then, from this reinforcement learning domain, you can actually use score function gradient estimation for any score function. And so it's the loss itself, we just call it a score function. And the nice thing about this framework is that only the distribution itself needs to be differentiable. And so it's a Monte Carlo approach. So what you will do is you will estimate the gradient of this loss function by taking a number of samples, like in the stochastic smoothing approach. And so for each of the samples, you're going to evaluate your score. Can be your loss, can be whatever, any type of score, doesn't need to be differentiable, with that prediction, and you're going to compute the quality. And that you multiply by the gradient of just the probability distribution. And so that's the beauty of this approach. Only this part needs to be differentiable, and this part you need to have a way to compute the score, to compute the loss. And so this works with predictions in the objective, prediction in the constraints, with any type of post hoc regret or a recourse action that you can possibly do. Except that it's reinforcement learning style, so it's pretty slow to converge. and and you need a lot of samples, and you might need a critic, and all of the dirtiness of RL comes up. But mathematically, it's very sweet. It's also been a bit difficult to get published in the conference trajectory because it works well, but it doesn't actually beat any of the specialized methods, right? It can do what 5 completely uncomparable papers can do, but it doesn't beat any of the 5 in there. Yes, a question?
So I didn't get, like, so you say it doesn't need to be in the objective, you can
No.
also have a certain
Yes.
constraint, but how do you deal with invisibility?
Yeah, so the idea is that you have a post hoc regret, for example, so that you have
Oh, you
a
just
feasibility correction. No. So to compute the loss is not the right word, but to compute the cost, you would include a recourse term or like a feasibility correction method, and then you need some penalty on that as well, right? And so the loss, the score, how good your solution is, will include both how much correction you had to do, right? So the stochastic point of
Okay,
view.
so it
and the
would be
original.
like a recourse, you assume that there is some feasible recourse that you can have.
Yes. Yes, yes.
So I had the same question. So in the end, you assume that you have complete recourse and you're penalizing the amount of recourse that you need to make the solution feasible, right?
Yes. Yeah, you can design it. It doesn't, yeah. But you have to design that part. Yeah.
But you assume that it's always possible to turn any solution to a feasible one if you pay enough in the recourse.
Yes, is that an...
Yeah, makes sense. I'm just curious.
Yeah, are there problems where that's not the
No.
case? Okay.
I don't think there are.
Yeah, what's up?
So when you're doing a solution, is it like a pair of X and penalty? Like, is it like solution and penalty, or is it like this penalty in the sense that you are just giving a solution and then an X and there is the penalty can be changed? Is it what kind of a solution do you give in this kind of a problem? So
You mean the Y, the true values?
yeah, so you just propose
Those are
Y.
typically the true predicted values, the true
Okay.
costs, the unknown costs. And then
Okay.
within that loss function, you do as you wish.
Yeah, so once you are in the deployment phase, you're
Yes.
getting a prediction model like this cost function, right?
Yes,
And then under this cost function, it will induce a different penalty to make the solution feasible. Is it like this?
yes, so you assume that at inference time, that you, for example, you take the predictions, you compute your solution, which is optimal according to those predictions. And then indeed, if you, well, in practice, you typically don't actually observe the true values, right? So you just deploy it and then you pay from your pocket. Yeah.
So you are not giving a prediction mod, cost function, which will ensure feasibility always.
No, the cost function, that one, a proper one should include a design where you
Okay.
penalize if the predictions lead to infeasibility. You don't have to, but you're gonna. Yeah, I just the recourse cost, or I mean like the actual objective function, including recourse. I think that's the best way to think about it. But you can design it as you way that you want. So there's many more. I'm actually putting this slide up because it raises a lot of questions that I would be happy to discuss. And so yes, we're doing sampling here, but this is not sample average approximation, right? We're sampling one set of predictions, and then we're solving that one. And then we're paying the recourse for that one cost. But if you want, you could actually do SAA in that. Sorry, you can actually do SAA in that score if you want. It's going to be a bit costly, but you could. And so I said that in this work, we just took a very simple distribution, simple Gaussian distribution. And that's because we only made it a distribution so that the score function gradient estimation technique could sample from it, right? So we don't actually care whether we're capturing the uncertainty properly because we're not doing SAA. We just want something to sample from, right? But what if you would care about capturing the uncertainty better? Right? So, okay. Let's come on. Yes. Okay. So the first key bottleneck was coming up with a good loss function. Plenty of work on that. The second, I think, key bottleneck is the efficiency, the scalability, namely that when you're doing this decision-focused learning, you're making a prediction, you're calling a solver, and only then you observe the loss and can back propagate. And so there are some works that are addressing this as well, and one of ours, which was based on a specific loss function, but made this observation that for the loss function we were looking at that point, we needed to have a cache of feasible solutions. And so what we would do is every time that we call the solver, we would store this because we used it in our noise contrastive estimation loss. And then we realized that, especially in the later iterations of training, we would call the solver, but the solution that it would give was already in this cache. Right? So if you make just small changes to your predictions, then in many of the cases the actual solution doesn't change, and it's part of this difficulty problem. And then we had the idea that, okay, why do we always call the solver? Maybe we should actually occasionally not call the solver and just take an approximate solution, just take the best one that's currently in our cache of feasible solutions. And it might not be the best solution, so there might be another one that gives you a better gradient, but at least there might be a good one, and it will give you some direction to backpropagate over. And so, surprisingly, this with a very simple choice rule of calling the solver only 5% or 10% of the time, we were able to get very good results on the problems we're looking at the time. Yes.
You try to warm start the solver with the cache solution.
Yes. So you have to definitely fill the cache with all of the optimal solutions of the true cost factors.
No, but I mean, they said that you were only 5% call the solver.
Yes.
You still warm start it with one of your cache.
Yes,
That's
in
the
one of the-
closest one, for example.
Yes, that's also true. In one of our earlier works, we were doing that. I'm not sure that we were doing it here. I mean, you still have to prove optimality.
But it's might be faster, right? Because you
Yes.
So you applied this to SPO?
Yes,
But
among
SPO,
others.
isn't it a subgradient, so it's not necessarily a descent method? Is the SPO, the gradient, is it a subgradient or is it a gradient?
It's a subgradient.
Yes, so it may not be a descent method, right? It may, the subgradient might not always be giving you a descent, and that's why, I mean, maybe cache might work better than SPO. Is it like this, or it
Well,
always works?
better than SPO. So our solutions don't actually get better; they just get a lot faster.
Okay, I mean,
Yeah,
faster, I mean.
Yeah, okay.
So what
It's
I wanted,
faster. It's not because the learning itself is faster, because you're simply not spending the time on CPU proving optimality.
okay,
I guess you still have a different position.
I will ask later.
Okay. So yeah, so on this black box method, which requires 2 solve calls, dramatic reduction in training time with very similar performance. This is for SPO plus, and then the SPO plus caching one is here. So yeah. Yes.
All the training is done on GPUs, I think.
No, we do everything on CPU because you have to switch back to CPU for the solver calling. Yeah, I mean now you have this final methods on GPU. Yeah, so actually we this one, if you don't do any solver calls, then you can just put the table in the GPU. But 0% doesn't work that well. You do want some solver calls.
I was asking because I was wondering if you don't use the CPU, you can be solving some optimization problem on the CPU and
Yes.
including your cache when you're training on the GPU.
Yes. That's yeah. I leave that to the engineering companies. But yeah, yeah. No, definitely yes. Yeah. Okay, so that was about. That was about contextual regression. I didn't press start.
Get 5 extra minutes if we rely on different watches.
But how long is the total time? Was it?
I think
An hour with question.
Yeah. Okay. Good. Okay, so something new on the menu, learning from historic solutions. And so that was about the parameters. But what if there's preferences that we want to learn? And so we started this work already quite some time ago, 2019, so we already graduated, with a small transportation company in Brussels. And so they had route planners, they had some commercial route planning software, and then they would make modifications to the routes before they would send them out to the drivers. And then that's because the problem was ill-specified, right? So they didn't bother putting all of their constraints into the commercial software. And they also didn't want to. And so then we thought, okay, maybe, and let's use AI, maybe we can actually learn what some of these changes are and then automatically apply them so that the routes are closer so that they have to do fewer manual changes. And not only do we want to learn these preferences, and we're using an effort, but we also want this to be able to adapt as the planners make different changes, that it adapts to the changes that those planners make. Yes, it's related to the Amazon Lost My Routing Challenge. 5 more slides and I'll make that explicit. This is earlier. Okay, so what's the idea? Well, clearly we will have the distance matrix because distance matters, but then we also have all of these historic solutions. And so can we somehow use machine learning to learn something from these historic solutions, inject that into the combinatorial optimization problem so that the solutions that we get both have low distance, but are also more similar to what they do by hand. Okay, and so for the learning part, what we did was, well, what you want to do is, given these historic solutions, you know that they like these solutions. So if you can fit some kind of probability distribution for which that those historic solutions have high probability, then you're able to learn patterns in that historic data. And so what we did was we took that sequence of stops. If you treat the sequence, then you can take a first order Markov approximation of that, which means that you'll get the probability of the depot, which is always 1, times the probability that from the depot they're going to a certain stop, and then probability that from that stop they go to the next stop, to the next stop, to the next stop, right? So this is a first order approximation. You only look at direct interactions. But the nice thing, there's 2 nice things about taking this first order Markov approximation. The first nice thing is that estimating these probabilities, you can actually just count. In historic solutions, you can just count how often in the past, when they went from a certain stop to another stop, you just increase that counter divided by the number of routes that has that specific pair in it. Then you need to add some parameters. Laplace smoothing, it's well known. Okay, so the estimation is very easy in this case. And then the question is, okay, can we now actually find the maximum likelihood routing? And the answer is yes. And so in principle, you have this kind of objective, namely you take the product of the probability of being in a stop and going to the next stop. But if you take the log, the minus log of the probability, you actually get a nice linear sum. And that linear sum is completely compatible with any routing solver that you use, because you now have a sum over all of the pairs of stops, and this minus log probability, you can just pre-compute it. So instead of having a distance matrix, you get a probability matrix. Namely, for every stop to every other stop, you get a probabilistic estimate. Okay, so that's nice because not only is it now a standard routing problem, and can use any VRP solver, including their commercial one, but you can also add the distance matrix to this. You have to normalize it, but then you can just add the distance matrix to it, and you can balance how much do you want to focus on the distance matrix and how much on this preference matrix. Okay, so is this an inverse optimization problem? Yes, this is an inverse optimization problem. And there are methods, recent methods called, for example, data-driven inverse optimization that use a cutting plane approach. But if you try to do a cutting plane approach over a VRP problem, you're quickly in trouble. So we had to redo it, and it didn't scale beyond 10 nodes. Okay, so you need some kind of pre-training method. Okay, and then in later work, we use neural networks. You can still do all of that. But I think one other important thing here, that the way, as I said, this company solves this problem day after day after day. And so the data set that you have, not every instance in that data set is equally important. The kind of manual changes that they did the past week in their mind is much more fresher, but also in their operations, it's much more important. And so what you can do, if you have relatively simple probability estimation technique, is that you can weigh each of your historic instances differently. And so give the more recent instances a higher weight and the older instances a lower weight. And so that's what we did. And actually with an exponential decay, this one gives the best results by far. Yeah, so it's a bit different from, you don't assume that all your samples are independent. You actually have some, well, they are independent, but you care about some more than others. Okay, so yes, this is related to the Amazon Last Mile Routing Challenge, which tackles a very similar problem, except that the type of information that you have about these is and so you, from each of the stops, you also know a bit about what zone they're in and what kind of goods there are. But many of the stops that in this challenge are visited only once. I guess I should have said this up front. This company has many regular customers. So let's say that they have like 100 companies that they supply to, and each day they visit maybe 20 of them. And so the companies will be somewhat different, but there's many recurring clients. And that's why we can learn these patterns. In the Amazon Last Mile Routing Challenge, this is not the case. Many of the stops are just one-off. And so you need a bit of a different learning approach. And so one of the methods that we looked at is, as most of the competitors did, let's split it up. Let's first try to sequence the individual zones, and then let's try to then solve a TSP within each of the identified zones. And so here, so the approach I just talked about was sequential, and we do the probability estimation, then we do the solving. Here we looked a little bit at integrated learning and optimization. So we used a structured perceptron, structured output prediction method to learn to balance. I think we had like 3-4 features. So the distance matrix, our counted matrix, and then some other property, like if it's in the same zone, like if it has the same zone identifier up to something like that. And so then you can use structured output prediction to learn that, and also there, and it works fairly well. Yes, are still okay? Okay, so that was for passively learning from historic solutions. And so very inverse optimization-like, except that in inverse optimization, people typically assume that the solutions that you're given are optimal, are the best. But when we talk to this company, they don't know what's best. And so there's probably better solutions, but the commercial software didn't give it to them, and they didn't find them while doing the manual changes. So there's still some differences, while a more generic probabilistic approach, I think, is suitable here.
I was just curious about that point, right? So this is really like an imitation perspective, inverse perspective.
Yes.
When you're estimating the probabilities based on frequencies and
Yes.
data, you will have zeros for any like conditional distribution from one stop to the, like any
Yes,
transition.
and seeing, yes.
Yeah, and so will you, let's say that one of the zeros is actually one of the better solutions, going back to what you were just finishing on now, right?
Yes.
So will you ever get rid of that, or?
Yeah, so two answers to that. First is that you should add some kind of base probability. And so with this
Okay.
alpha,
So
you
have
add
like
a pseudo counter. Yeah,
Okay.
you add like a prior. That's the first thing. And then the second thing is that okay. How do you evaluate, right? So if you have your training data set and then your testing data set, what we saw is that purely optimizing the learned probabilities works best.
Yeah, because
But-
that's what you have in your data.
Yeah. But I would never deploy this, right? So I think the right thing to do is to combine these with your distance matrix, so that in case this one is uninformative, it's the base prior, so that then the distance matrix is actually leading, right?
Okay.
So, but the problem is when we evaluate it, this one never is better, but it's definitely the right thing to do in practice.
Yeah, that's my question. Like when you do this test time, right?
Mhm.
I didn't do the Amazon challenge. I don't even know how they measure the real winner, right? So I mean, you know, in the past, but then do you have like hidden good or bad? But if you produce a route that nobody never scored good or bad, how do you know whether that's like you need to
Yes.
give to a real driver in theory?
Yes, that's a counterfactual evaluation, which is always tricky indeed. So in this case, they had a penalty where they did assume that, so for the unseen test set, they would have routes that were actually deployed, and then they would have a penalty function that measures how many are different, but it also takes the distance of those that are different into account. So if your solution is mostly the same and you do a slightly different order and the difference in kilometers is tiny, you will actually score very good. Yes.
So you have to do about the same order, but don't care too much about the kilometer as long as the order. It's similar, right?
Well, so even if the order is different, it will matter how many kilometers you're off. And so I think that's a fair way to compensate a bit for that. But it again shows that actually also in their setting, they cannot make any guarantees that their historic solutions are the optimal solutions. And so, which is this basic principle of inverse optimization. Okay. All right.
One tiny question, like, do you think this could, I don't know if you saw the UPS, like no left turn.
Yeah, that's
Like when you learn something like that, I suppose you don't know you're not supposed to turn left, but there is a policy and you're supposed to turn left and the drivers are actually not doing it. You learn.
Yeah, so the no turn left policy, it's really about street level routing, right?
Yeah.
And this is about like stop sequencing.
No, but that could influence, right? So you know that because you're gonna turn left, you can't really easily go from there to there without doing like this. And then if you go like this, you might as well visit that.
Right.
My point is that, let's say there is a hidden no turn left and then the drivers are following it and then you observe their different order because of that.
Yes.
We kind of infer the ground rules.
Yes, I'm not entirely sure. My hope is always that it's somehow learning a penalty on top of the distance matrix, which will say that, okay, this one is 5 kilometers, but you know, they like it, so let's call it 4 kilometers. It doesn't actually do that, but that's how I'm hopeful that yeah. So okay, so what I just talked about assumes that we have historic instances that are preferred. What we also look at is, can we actually learn by asking a user, by showing a user two solutions and asking them which of those you think is best. And so we don't have historic solutions. We're going to ask a user which of those is best. And so it's like an active inverse optimization problem, active preference running for combinatorial optimization. We will make an assumption that it's a multi-objective optimization problem. So we already have different sub-objectives that qualify the quality of the solution. So this work came from a work with a steel company. And so it matters how you order the different products and like the machine degradation and the quality and so forth. So they had different kinds of measures. And then the question is, can you learn a linearization of these sub-objectives so that the solutions that come out are actually preferred by the user? And so a general framework for this type of active problems is called constructive preference elicitation by Dragona et al. It's an extension of this of the perceptron algorithm actually. And so you start with initial weight estimate, and then for a number of iterations, you will be told what your problem instance is. You will generate two solutions in some clever way. And then you will ask the user, which of those do you prefer? And then based on their answer, you will update the weights of your linearization. And then you will do this for a number of times. And then at inference time at the end, you will actually compute a solution that is best according to this linearization. Okay. So the two key parts are this weight update and selecting the query. And so the weight update in its general form it's like a gradient update, right? So you have your weight, and then you have the learning rate, and then you have another weight that I will explain soon, and then you just take the difference for each of the sub-objectives, also the sub-gradient, you will take the difference between those sub-objectives. And this is the solution that the user chose, and this is the other one that you show to them, which should be worse. Okay, so all the weight update can be generally specified like this. And then Marianne, the postdoc who worked on this, she observed that actually if we formulate it this way, then there's many different methods, both in inverse optimization, but also in other techniques that fall under this framework. So the original preference perceptron, it would set this weight to 1. So that means that it would always take, if a user preferred this one, this solution, it would always take the difference between the sub-objectives pushed in. But if you look at the structured perceptron algorithm, then that one would first check, is the solution that the user preferred, is it already better scored with our linearization than the other one? And so does the function already prefer this one? In that case, don't backpropagate over it, don't update the weights. And in the other case, then you do update the weights. So this preference perceptron is like InfoNCE, it's like a contrastive method. It tries to push away the two always as far away as possible, even if it already agrees, it will keep pushing them apart. The sub-perceptron will only do that if they disagree. And then what I like a lot is that actually I challenge her with these direct preference optimization papers that use in large language models. So in large language models, when they learn preferences, what they do is they assume a Bradley-Derry preference model, and they also have two answers to a prompt. And then what they do is they backpropagate over, they actually try to maximize the likelihood of this Bradley-Derry preference model according to that answer. So it's like a sigmoid over these utilities. And it also fits within that framework. And it's indeed, as I said, by taking the sigmoid over the difference in utility of the entire solution, and it gives you like a smoothed variant. That's how you can interpret it in this case. So that's both mathematically and in practice, I think that's very nice. Regarding selecting the query, and so your algorithm has to present two solutions. And so the first solution, that's also what the baseline, this is the baseline method. So the first solution is just the best solution according to the currently learned linearization. And then the second one balances off being good according to the current linearization, but also being somewhat diverse with respect to the previous query. And if they're identical, you don't want that, but if they're too similar, you're not going to get a lot of signal. You might want them to be a bit more dissimilar. And so their diversity measure was like the L1 norm between the sub-objectives, because they're actually calling a solver. And so if it's not linear, you're going to spend a lot of time waiting. So that's what they did. So it requires you to twice solve this potentially NP-hard problem. And so in this paper, which will be at HCI 25, we actually pre-computed a large number of solutions up front. And that means that we now no longer have to restrict ourselves to linear. We can actually use richer utility functions, acquisition functions. So we're going to use to look a bit at RL style research, upper confidence bound based acquisition function, and some additional clustering. I hope I included results. Yes. So doing this MLE approach, so like the direct preference optimization over LLMs, if you combine that with this UCB-based approach, then it actually performs really well. You get lower regrets, you get fewer queries, and you get more often that the decision maker actually agrees with the learned linearization. All right. The dessert. So the dessert is more LLMs, or is proper LLM this time. And so another, like, with the way that the AI field has been evolving, and it's not just about the parameters, you may wonder where actually does the structural formalization come from? And so who translates this problem description to the formal model? So this requires modeling expertise. And can we actually use large language models to support formally model these type of problems? So this is an excerpt from the NL for opt dataset, which was a NERC dataset a few years ago. It has linear programs with up to 4 decision variables. Absolutely, ladies and gentlemen, groundbreaking. And so, but yeah, I mean, the dataset is from before LLMs actually. And so we looked at different ways that you could model this. So can we use LLMs to directly come up with a solution? Luckily, the answer is that's really bad. Can we ask it to directly model the formulation and give that to a solver? Shall we instruct it like we do our students and tell it that there should be a decision variables and constraints and objective and only then feed it to constraints and so forth? Or do we do like old school NLP and do we tag entities based on their expected relationships? And so in that work, it was CP24. So we did in-context learning. And then the question is on what kind of data sets do you evaluate it? So there was an NL for op data set with up to 4 variables, and then the logic grid puzzle data set. And so we thought, okay, let's, we were also, I was going to take over a course from a colleague about constraint modeling. And so we thought, let's give it the exercise sessions of that course. And let's first try different methods on these understood data sets, and then let's put it to the test. So I think one thing is that a lot of people in combinatorials at large, they've been playing with LLMs, but I think what we need is we need a better structural evaluation of the capabilities of these methods to help in modeling problems. And so that means automatic model evaluation, but it quickly becomes tricky. And so if you also let it choose the decision variables, then how will you evaluate it? Because your ground truth model will use whatever decision variables, but the LLM can choose any name or even any view on the decision variables. So if you do, should you prompt it to tell it and so forth and so forth. And also what to measure? Are you going to just measure the accuracy of the solution? Or do you want to measure whether it's actually semantically equivalent? Lots of interesting questions. So some results of that CP24 paper. So on NL for opt, you get around 11% of the LLM directly in 2024. 11% accuracy, which is very low. And then if you ask it to model it directly, you get around 81%. And if you tell it, like be structured and do first the decision variables and the constraints, you get around 84. And also for logic grid puzzles, the values are a bit lower, but these are fun results. And then we thought, okay, let's now give it some of the problems that we care about, that we teach our students to solve. And then you see that in the first exercise session, the easier ones, LM is still doing pretty fine. Then in the second exercise session, which becomes more involved, it's getting a bit worse and a bit worse and a bit worse. So this really shows that, first of all, we don't have good benchmarks. And second of all, there's more work to do. And so since then, we've built a larger set of benchmarks. We have around 100 now. Other people in constraint programming have also done some work, and in combinatorial optimization also some more data sets that good. Another thing that's also changing is that we now have agentic frameworks where you don't just have to ask the LLM and then execute it answer, but you can ask the LLM, you can give that and have it call just a Python interpreter or whatever, and then if there's some error, feed it back into the LLM and output it to multiple sampling. All of these things that people do in coding LLMs can also be applied here. And then we also tried with different modeling libraries directly in our tools, using our library, using Reason. And so you do see that the kind of tools that we build to make life easier for modelers also tend to get higher accuracies for LLMs. Many more things possible here. Okay, so what's the bigger picture? So my research agenda, my research goal is that the traditional way of using model plus solve is that the user writes the model and then calls the solver. But I think it's very interesting to also look at underspecified problems, to learn, to make some of the predictions, to learn user preference, and to integrate that into the optimization. I'm also very interested in explaining solutions to constraint solvers. I didn't talk about that, but that's also something that I do. And then I hope that one day we can make this interactive, stateful, maybe even natural language. And that's the goal of this ERC Consolidator grant that I have. Okay, so that's what explainable constraint solving looks like. Happy to talk to you more about that. And that's our platform. And those are the takeaways. Thank you very much.